In this video, we are going to take a look at our exponential functions. We're going to graph a couple of them and talk about some of our definitions. So let's start with just our general definition of an exponential function. Exponential function is going to have the general form y equals a times b to the x. And we've got a not equal to 0, b greater than 0, and not equal to 1. Basically, the thing that's making it an exponential function is that your variable x is in the exponent position. So that right there is what makes it exponential. Now let's talk about what are a, b, and we'll talk about x as well, although x is still just your independent variable. Y is your dependent variable, just like with our linear functions and our quadratic functions. A is going to be our initial amount, or our y-intercept. So if x is 0, your y will be equal to a. Makes it nice and easy for us to pick out our y-intercept right away. B is going to be the base, or the common ratio. Let me fix that. Okay, that's better. So common ratio. Basically, it's what you're multiplying by to get to the next term. And then x is your independent variable. And again, y is your dependent variable, just like in our other functions. So we talked about how to come up with the table of values for our functions. So I'm going to go through this part kind of quickly, only explaining a little bit. Here I am graphing the function y equals, or f of x equals 2 to the x. So I'm going to come over here and put it in my table of values. And what I'm going to do is I'm going to start with 0, just because it's easy to plug in. So I'm going to go 2 to the 0, which is 1. 2 to the 1, which is 2. 2 squared, which is 4. 2 cubed, which is 8. And 2 to the 4th, which is 16. Notice that to get to the next term, I'm multiplying by 2. Multiplying by 2. Multiplying by 2. So our b here is the 2. Notice the a is 1. A is your y-intercept. There's nothing there in front of the b to the x. Notice here, 1 is your y-intercept. Now, remember to go the other way with our negative exponents. A negative exponent just means to drop to the denominator in this case. So 2 to the negative 1 is equal to 1/2. Notice it's the reciprocal of 2 to the 1. So all I'm doing is taking these on this side and flipping it. So it's the reciprocal of that one. 2 to the negative 2 is 1 over 2 squared, which is 1/4. 2 to the negative 3 is 1 over 2 cubed, which is 8, so 1 over 8. And 2 to the negative 4 is 1 over 2 to the 4, which is 16. Okay, that got a little messy. Take a minute to get those written in, and then we're going to plot these points. So remember, our table of value, what we've done is we've created points. We've created points for us to graph, which I'm going to do now. All right, so 0, I'm going to start here. 0, 1, 1, 2, 2, 4, 3, 8, and I'm not going to plot the 16. No, I actually need to go a little smaller. All right, going the other way, negative 1, 1/2. It's going to be about halfway in between there. Let's move it up just a little. And then negative 2, 1/4. Let's make it bigger, which will be about right there. And then it's going to continue getting smaller and smaller. It's going to keep getting closer and closer to that x-axis, but not really cross it. So I'm not going to plot the negative 3, 1/8 or the negative 4, 1/6, because it's going to get too close to that. So I'm going to go ahead and connect and extend through. Now remember, it's important here. Let me redo that. Okay, I'm going to redo it with a thinner line because that was too messy. It is important here to remember we don't cross that x-axis. I go right up along it and then whoosh. You obviously don't need to make such big dots. I was just trying to make mine obvious. Okay, so let's look at our domain and our range. So domain, remember, is our x-coordinate, or our x values, our input values. And just like with our quadratics and with most of our linears, our domain, we can plug in any value for x. So this is going to be all real numbers. That's going to pretty much always be true for exponentials, unless it's an application problem. Now, the range is the y values. So my y values don't dip below the x-axis. So my y is going to be greater than 0. Not greater than or equal to, because I'm not dipping below. I don't touch the x-axis. I don't dip below. But I have a graph above the x-axis. Well, at the x-axis, your y is 0. So in this case, y is greater than 0. I do want you to notice here, as your x values get smaller and smaller, so as they come this way, I'm going to get closer to but not cross that x-axis. So notice as the x values decrease, the graph of the function approaches but does not cross the x-axis. This is called an asymptote. So an asymptote is a line that a graph approaches but does not cross. And in this case, our asymptote is the x-axis. And the equation of the x-axis is y equals 0. So that's just two different ways to say that my graph does not cross the x-axis. Okay, so this is our first exponential function. Notice it's growing from left to right. Now we're going to look at our at another example. So example 2. This time we have y equals 2/3 to the x. Notice the parentheses. So the whole thing is being raised to the x. So my function for my table of values is 2/3 to the x. And once again, I'm going to start at 0. So it looks like, well, oh my goodness, we have a fraction. Oh no, this is going to be difficult. It's not going to be difficult. 2/3 to the 0. Anything to the 0 is 1. 2/3 to the 1 is 2/3. Okay, 2/3 squared. So don't let that exponent with the fraction scare you. Remember what you're going to do is do 2 squared is 4, 3 squared is 9. And let's do cubed. We're not going to do to the 4th because we're not going to be able to plot it anyway because it's going to get so tiny. 2/3 cubed. 2 cubed is 8 over 3 cubed is 27. And again, remember what we're doing here is just multiplying by 2/3 each time. 1 times 2/3 is 2/3. 2/3 times 2/3 is 4/9. 4/9 times 2/3 is 8 over 27. Now, here's where that negative exponent really comes in. Because 2/3 to the negative 1. All I'm going to do is come down here to the 1. And I'm going to take what I had for that one and I'm going to flip it. So that's what the negative tells me to do. So 2/3 to the 1 is 2/3. 2/3 to the negative 1 is 3/2, which is 1.5. For 2/3 to the negative 2, I'm going to come down here to 2/3 to the 2. 4/9, and I'm going to flip it. So it's going to be 9/4. I'm going to write these as decimals to make it a little easier to plot. So 3/2 is 1.5. 9/4 is 2.25. Then 2/3 to the negative 3. I'm going to come down here to 2/3 to the third, which is 8 over 27, and I'm going to flip it. So 27 over 8, which is going to give me 3.375. We're going to have to do a little approximating on this one. All right, let's plot these points. I'm actually going to start with the negatives this time because those numbers are bigger. And then once I get to where I'm having trouble plotting them, I'll just follow that general exponential graph shape. So I'm going to start with -3, comma, 3.375. So -3, comma, 3.375. So about right there. -2, comma, 2.25. So about right there. -1, comma, 1.5. 0, comma, 1. 1, comma, 2/3. 2, comma, 4/9. That's just slightly less than half. And then 8 over 27 is going to be really small. So I'm not even going to plot it. I just know that it's going to, as I connect, follow right along that x-axis, but not actually cross it. Okay, my domain, once again, all real numbers. In my range, once again, my x-axis is my asymptote. So all my values for y are greater than 0. Now this time, I said, notice that as x values decrease, the graph of the function. But what I should say is as the x values increase. So this time as my x values get bigger and bigger, so as my x values get bigger and bigger, the graph of the function approaches but does not cross the x-axis. So this time as the x values increase, the graph approaches but does not cross the x-axis. Okay, we are going to do example 3 together in class, so you're just going to save that one. You don't need to worry about trying it on your own, and that is going to be that.